Welcome to today's Explainer. So imagine for a second being a scientist at the very end of the 19th century. Humanity has the laws of motion mapped out, we've got a handle on gravity, and electromagnetism beautifully defined. Honestly, a lot of scientists back then genuinely believed physics was, well, basically finished. They thought we'd hit all the major milestones and all that was left was just, measuring things a little more precisely. But there was this one lingering, kind of minor-seeming mystery, just a tiny mathematical puzzle about how hot objects glow. And when they finally pulled on that loose thread, the entire fabric of classical physics completely unraveled. Today we're going to look at this massive historical mystery that totally broke the known laws of physics and the brilliant mind that literally had to put the universe back together.
To really grasp the scale of this revolution, we first got to ask what actually happens when the established, time-tested rules of classical physics just outright break. For centuries, classical physics worked perfectly, right? You heat something up, it gets hotter. It gets hotter, it glows. First red, then yellow, then white. Simple enough. But when the brightest minds of the era tried to use their trusty classical equations to calculate exactly how much energy a perfectly glowing hot object should emit, the math spit out a completely impossible scenario. It literally predicted that any hot object, even your kitchen oven, should be pumping out infinite amounts of energy at shorter wavelengths, like a world where just looking at a glowing ember would instantly vaporize you with radiation. Obviously, that doesn't happen. So they knew right then their fundamental understanding of the universe was profoundly flawed.
Now, the scientific community gave a wildly dramatic name to this problem. They didn't just call it an anomaly or a glitch, no. They called it the Ultraviolet Catastrophe, which is just an incredible term for a mathematical error, don't you think? They used the word ultraviolet because this infinite energy prediction spiked spectacularly as the radiation's wavelength got shorter, pushing right past visible violet light and into the invisible ultraviolet spectrum. It was a true catastrophe for classical physicists. Their most trusted, ironclad equations were telling them something that completely contradicted everyday observable reality. They were literally stuck at a dead end.
Okay, let's dive into the specific theoretical object they were studying when everything fell apart. To keep the math as pure and simple as possible, physicists imagine this idealized concept called a blackbody. So a blackbody is a theoretical object that does two very specific things perfectly. First, it absorbs absolutely all electromagnetic radiation that falls on it. No reflections, no light bouncing off, nothing. Second, when it gets hot, it emits radiation perfectly, and that emission depends entirely and only on its temperature. It's completely independent of whatever material it might be made of. By focusing on this idealized blackbody, physicists figured they could isolate the absolute purest laws of heat and light.
Now I know, an ideal theoretical object sounds incredibly abstract, but we actually interact with approximations of blackbodies all the time. Think of a hot iron rod in a blacksmith's forge. When you heat it up, it glows with a specific color that's tied directly to its temperature. The hotter it gets, the brighter and whiter it glows. Or, even our own sun is an excellent approximation of a blackbody. It absorbs practically everything that hits it and radiates immense energy based purely on its scorching surface temperature. So while the blackbody was this simplified mathematical tool, it described very real, very vital phenomena in our universe.
Let's put this conflict right in front of us. This is the ultimate showdown, classical physics versus reality. On one side, we have classical theory, which dictates that as the wavelengths of emitted light get smaller and smaller, the energy should climb higher and higher, shooting straight up to infinity. But then, on the other side, we have reality. In reality, a hot iron rod or the sun emits finite, measurable, totally manageable energy. The radiation peaks at a certain color and then just gracefully drops off as you move into the ultraviolet spectrum. The equations said infinity, reality said finite, and in science, when the math fundamentally disagrees with what you can see with your own two eyes, well, the math has to change.
So the crucial point here is that just tweaking the old equations wasn't going to cut it. The classical worldview, this idea that energy flows in continuous unbroken waves, was actually the very thing causing the catastrophic prediction in the first place. The scientific community was absolutely desperate for a solution. They needed someone willing to break the fundamental rules, toss out the classical assumptions, and introduce a radically new way of thinking about how the universe actually operates down at its most microscopic level.
Enter the year 1900, the dawn of a new century, and quite literally, the dawn of a completely new era in human understanding. In this specific year, a German theoretical physicist named Max Planck decided to try something radical. Now, Planck wasn't a rebel by nature. Actually, he was quite a conservative physicist who deeply respected the classical laws.
But he was just so frustrated by the ultraviolet catastrophe that he decided to try a mathematical trick, a desperate act, as he later called it. He just wanted to force the equations to match the experimental data. He had no idea at the time, but this mathematical hack he introduced in 1900 was about to change the world forever.
And here is the breakthrough. To make his math match reality, Max Planck proposed that energy is not continuous. Instead, energy is emitted or absorbed in small, discrete packets. He called these tiny, indivisible packets quanta. Think of the word quantity. He was essentially saying energy comes in specific, countable quantities. You can't have half a packet of energy or a quarter of a packet. You can only have 1 or 2 or 3 entire packets, no in-betweens.
This really brilliantly illustrates the massive paradigm shift. I want you to picture the classical view as a smooth, continuous ramp. You can stand at any possible height on that ramp, right? That's how they used to view the flow of energy, smooth and unbroken, like a flowing river. Now look at Planck's view. It's not a ramp, it's a staircase. You can stand on the first step or the second step, but you absolutely cannot stand hovering perfectly between the steps. Energy is granular. It clicks into place in these discrete packets, these quanta. It sounds like a simple change in perspective, but by making energy a staircase, Planck perfectly solved the ultraviolet catastrophe. The math finally matched reality.
But Planck didn't just propose some abstract philosophical idea. He backed it up with elegant mathematics. He distilled this mind-bending concept of granular energy into a single, breathtakingly simple equation. Honestly, it's an equation that stands right alongside Einstein's E equals mc squared in terms of how completely it revolutionized our understanding of nature. And here it is. E equals h times f. 3 little letters that basically birthed modern physics. This equation is the defining climax of the whole mystery we've been talking about. It proves mathematically that energy and frequency are locked together in a very specific, quantized way. It is elegant, it's incredibly concise, and it's the absolute bedrock upon which all of modern quantum theory is built. Let's systematically break down what we're actually looking at here so we fully grasp its power. The E stands for the energy of one single quantum, one individual packet of energy. The F stands for the frequency of the radiation, meaning how fast the light wave is vibrating. But the real magic? That's the H in the middle. That is Planck's constant. It is an unbelievably tiny number, but it's a fundamental limit of our universe. It dictates the exact strict size of those energy stairs we talked about earlier. Planck's constant is the exact conversion factor that binds the frequency of a wave to the energy of a quantum packet. So what does this actually mean in a practical sense? Well, this equation dictates a direct relationship. Higher frequency equals higher energy. Because H is a constant, if you increase F, the frequency, you automatically increase E, the energy of the packet. This perfectly explains why ultraviolet light, which has a very high frequency, has much higher energy quanta than infrared light. It's the exact reason why that glowing iron rod shifts from red to yellow to white as it gets hotter. The energy packets are literally packing a bigger punch as the frequency goes up. But unlocking the secret of quanta wasn't just some abstract academic exercise. By realizing that energy functions in these discrete packets, we gain the ability to actually manipulate and control energy on a microscopic scale. This single realization became the spark that ignited an unstoppable technological revolution.
Just consider these real-life applications that literally only exist because of Max Planck's discovery. LED lights, which illuminate our homes and phone screens with incredible efficiency, they rely entirely on the precise jumping of electrons between quantum steps to release discrete packets of light. Lasers, which we use for everything from eye surgery to scanning groceries at the store, are just concentrated, synchronized beams of quanta. Entire fields like quantum electronics and advanced thermal radiation studies trace their direct lineage right back to that E equals HF equation. Basically, every time you turn on a modern device, you are interacting with technology built on the concept of quanta.
Stepping back to look at the big picture, this explainer highlights how Planck, proposing that energy is emitted in tiny packets, essentially birthed entirely new scientific disciplines. His mathematical trick to solve blackbody radiation became the absolute foundation of quantum mechanics. It paved the way for atomic physics, allowing scientists like Niels Bohr to actually map the atom. It made modern electronics possible, giving us the semiconductors that power all modern computing. Max Planck didn't just solve a 19th century math problem, he handed us the blueprint for the 20th and 21st centuries. Which brings us to a final, thought-provoking question. We've seen how the discovery of quanta took us from a catastrophic breakdown in classical physics all the way to the lasers and supercomputers of today. But the quantum world is notoriously weird.
counterintuitive, and still full of profound mysteries. If the very light we see and the heat we feel are all just an illusion of continuous flow, built on a reality of tiny, indivisible packets, what other fundamental quantum secrets are just waiting out there for the next bold thinker to unlock? Thank you so much for joining me for this explainer. I really hope this sparked your curiosity, and I highly encourage you to keep exploring the incredible, granular universe around you.